And with that, I'll go ahead and turn it over to first speaker, and it's David Smith.
It's a pleasure to be back in Providence again. I want to talk about some of the stuff that we've been doing at the Mayo Clinic. I hope this talk isn't too remedial for most of the people in the audience. So I'm going to go through it very quickly. If people, it's a little bit about the history and background, just a little bit about myself. I'm a professor in lab medicine and pathology at the Mayo Clinic. I'm also the director of the Technology Assessment Group, which is responsible for looking at new technologies and their potential impact. I don't have to run any of the cores. I just have to give people advice whether they take it or not. Actually, frequently they don't take my advice, but that's fine. This is what I want to talk about, a little historical stuff, the Human Genome Project, the evolution of next-gen technologies, and the most important thing that I want to talk about, because the only way I'm going to get the attention of the Mayo Clinic is to demonstrate that this technology will impact clinical practice, is what we've been trying to do, because Mayo Clinic is not a big dive-in head-first kind of place. They kind of stick their pinky in, step back. Actually, they'd like somebody else to stick their head in first and get it cut off, and then see what are the problems. And there's going to be a lot of problems with getting this technology in the clinic. What is going to be actionable? What are you going to do? What are you going to report to the patients? So I'm going to try to get through these things. I saw how many slides there were, and I'm clearly not going to do it all. So I'll just keep talking until somebody puts their hand up in the back, and I'll stop at that moment. The human genome is basically the 3 billion base pairs you got from your mom, the 3 billion base pairs you got from your father. Men are genetically deficient. If you didn't know that already, it's true genetically too. 23 pairs of chromosomes, 22 autosomes in the sex chromosomes, and they range in size from 42 million to about 240 million base pairs. The whole plan of the Human Genome Project, it's kind of an interesting point in time, because if you're old enough, it was a big deal, and if you're young enough, you just accept it as we've always known about it. But it is a big deal. I'm old enough to remember Gregor Sutcliffe, and his PhD thesis was to sequence PBR322. Today, you could sequence everyone in this room, and it wouldn't be worth one PhD. That's just the way technology moves us forward. But the idea was to develop the technologies to sequence something as complex as a human genome cheaply and affordably, and to start with simpler genomes. So it was kind of exciting when they started and they sequenced the first plasmid, and then they sequenced the first, tiny thing, virus, bacteria, and worked their way up, and how exciting, blah, 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 blah. The interesting thing is that if you move up the evolutionary ladder, if you go from some of the simpler organisms towards human, less and less of the genome is actually responsible for the coding of protein. In us, we're only about 1.2% of our genome actually codes for protein. And if you look at what our genome is comprised of, it's 45% repetitive sequences, and those really present quite a challenge, depending on their distribution and where they are in the genome, for actually making and assembling a complete human genome. The challenge was to be able to do this affordably, but not to do it at 100% accuracy, because it was an asymptotic point in terms of how much it would actually cost. They decided on something like 99.99%, but even at that level accuracy, you put in 10,000 errors in the genome that you assemble. They wanted it to be fast, multiplexing, affordable, and it was a big deal, again, if you're old like me, to see the evolution of something like this, the CE3700, a 96 capillary device that you could just keep running the capillaries over and over again. And with the vision of Craig Ventnor to put it at 330 of these in a room at Celera Genomics, and then to take all the data that the public genome generated and steal it and use that to assemble a genome sequence, it was a very